Hello and welcome everybody to a video on the foundation degree in integrated engineering. This video is based for mathematics and control, and we're going to be looking at first order differential equations. Now the first order differential equation is a relatively straightforward differential equation, but there's some techniques we need to get down. So here's a couple of worked examples to help us. Now if we look, there's two forms of the equation that we're going to focus on, and we're going to start with the separable equation. It's called a separable equation because if we look at the form that the equation takes, it will be something like this, where we've got on our left hand side the derivative function, in this case ds over dt, and we've got on the right hand side of the equation a function of time, which in this case is 2 plus 3t. So with this function, obviously we have no boundary conditions, so all we can do with this is look at this in terms of the general solution. And with the general solution, the first thing we do is separate our derivative function, our ds dt. So what we're going to do is do that, and you see what we do is we bring ds to the right hand, we leave ds on the right hand side, and we bring dt to the left hand side. Okay, we just multiply it up from there to here. Okay, now we have a function ds on the left, a function dt on the right. We can't have those functions on their own, and what we need to do is integrate both sides. So what we're going to be doing is integrating 1, because we've got 1 ds. So we integrate 1 with respect to s, and we're going to integrate 2 with respect to t, and 3t with respect to t. So what we get, the integral of 1 with respect to s is s, the integral of 2 with respect to t is 2t, and the integral of 3t with respect to t is 3t squared. And always remember, we must add on when integrating our constant of integration, c. Now we don't know what c is with no boundary conditions, but if we put boundary conditions in, then we can calculate c. So let's just do that. So our boundary conditions are that if t is 0, s is 0. If we plug that in here, what that's going to prove to us is that when t is 0, s is 0, c is also 0. So we get that solution. Now we're going to look at the non-separable differential equation. This one's slightly trickier. Again, I've put the boundary conditions in here at the start to say that at t equals 1, I equals 0. We're looking at a resistance of 100 ohms, we're looking at an inductance of 100 millihenries, and we're looking at a supply voltage of 50 volts. Okay, so looking at that setup, if we use Kirchhoff's voltage law, what we develop is that the voltage coming from the supply is equal to the voltage across the resistor, I times R, plus the voltage across the inductor, L times di dt. We know what R is, we know what L is, so we know what V is, so we can populate that equation to get a slightly different differential equation. Now this one's slightly trickier because our di is on the same side as an I function. So we can't just separate this derivative function. We can't just take that dt up there, okay, because when we try and integrate, this 100 isn't going to be integrated. So what we need to do is bring in a few equations to help us. These are standard equations you'll find in pretty much any textbook, and it's basically saying, right, if our equation is in this form, where we get dy over dx plus some function of x times y is equal to another function of x, then our answer, our value of y, is going to be solved using this equation. And mu in this equation is calculated as e to the power of the integral of p dx, or dt I've put in this place. Okay, so let's look at our example, see how this works. Okay, so here's our equation. 50 is 100 it plus 0.1 di dt. Now the first thing we need to do is what's called normalize the equation. Normalizing the equation means making dy dx, or your derivative function, equal to 1 times itself, basically. So we only want dy dx here. Currently we have 0.1 times dy dx in our example. So what we need to do is get rid of this 0.1. We don't want it there. So all we do is we divide everything else in the equation by 0.1, and what we get is that 500 is equal to 100 I times I of t plus di dt. From that we can now compare with this equation at the top, and we can determine what our p and what our q are. And from it we can see that p is equal to 1000. You see it's p of t in our example because we are with respect to t in our derivative, and q is equal to 500. So we've got our p and we've got our q. We need to mind our p's and q's. Right, taking this, then we now can work out what mu is because we've got what p is. So that's the next step. So let's have a look. So mu is e to the integral of 1000 dt, because p was 1000. Integral of 1000 with respect to time is 1000 t, so mu is equal to 1000 t. Now we put mu into that third equation on our previous setup, so we get mu times I, and I is what we're after in this solution, is equal to the integral of q times mu, and I've written it that way round to be more mathematically pleasing on the eye. Okay, so mu times q of x. Okay. So now we can integrate this 500 e to the 1000 t with respect to t. That's very straightforward. Divide by the 1000. So we get that e to the 1000 t times I, and I is what we're trying to get this to be, is 0.5 e to the 1000 t plus our constant of integration c. Please do not forget this c, because this is what will cause your solution to be wrong if you forget to include this. Right, so now we plug in our boundary conditions. I was 0 when t was 0, so what we get is that 0 is equal to 0.5 plus c, so c must equal minus 0.5. Okay, so now we've got our c. We're on the last step of this solution. Plug everything into that equation, and now we just need to divide through to get I of t on its own, and that we just divide by e to the power of 1000 t. You can see here e to the 1000 t and e to the 1000 t will cancel, and here what we're going to do is use the rules of powers that say if we have a division by something to a power, we can take this function to the top of the division, but we have to make it a negative power, and that's where we get our solution for our differential equation. And if you look at that and then compare that to the Helmholtz equations they give you in the books, you can see where Helmholtz derived it from. Okay. So there's two very quick worked examples on how to solve first order differential equations. I hope that's been helpful for you.